Good day everyone. In this video, I will present my numerical methods application developed using Python and MATLAB. The first is my preferred language, which is the Python. This application is designed to solve different mathematical problems involving root finding methods, matrix operations, graph visualizations, iteration tables. The program uses Python libraries such as tkinter for the graphical user interface, NumPy for mathematical computations, and Matplotlib for graph plotting. At the beginning of the program, several Python libraries are imported. The Math library provides basic mathematical functions. The RE library is used for regular expression, which help in format mathematical expressions and entered by the users. The tkinter library creates the graphical user interface or GUI. And for NumPy, the library handles numerical computation and matrix operations. And the Matplotlib library is responsible for plotting graphs and visualizing roots. The style used, it applies a dark grid style to make the graph look cleaner and viewable. The function called normalize expression prepares the equation entered by the user. For example, x squared minus 4 equals 0 is automatically converted into a Python readable format. This function performs several tasks. It replaces the caret symbol with double asterisk, converts uppercase x into lowercase, converts equations into expressions equals to 0, automatically inserts multiplication symbols. For example, 3 in 3, the x plus 2, it becomes 3 asterisk x plus 2. In parse function, it converts the mathematical expression into executable Python function. Inside the function, the recival is used to compute the equation safely. Only approved mathematical equations are allowed, such as sine, cosine, tangent, logarithm, square root, and exponential function. These allow users to input many types of equation, including the polynomial equation, trigonometric equation, exponential, and logarithmic equation. The function refine root improves root accuracy using the bisection principle. It repeatedly divides the interval into two parts until the root becomes highly accurate. Next is the finding root intervals. The function find bracket searches for intervals where sign changes occur. A sign change means fx1 times asterisk fx2 is less than to 0. It indicates that the roots exist between the 2 points. The function scans many sample points inside the interval provided by the user. Another function called find bracket auto automatically expands the search interval if no root is found initially. This involves the reliability of the applications. Next is the numerical derivative. It estimates the derivative numerically using finite difference approximation. The formula used are on the highlights, are the highlighted one. Next is the find root detection. The function find all roots searches for all possible roots inside the interval. It combines sign change detection, root refinement, and Newton method sweeps. This helps detect the simple roots, repeated roots, and tangent roots. The detected roots are stored and displayed in the interface. In matrix operations, these several functions are included for matrix computation. These include addition. It adds two matrices element by element. Multiplication performs matrix multiplication using NumPy. Transpose converts rows into columns. Determinant, it computes the determinant of a square matrix. In inverse, it finds the inverse of a matrix. In adjoint, computes the adjoint matrix using cofactors. In matrix power, it traces a matrix to a selected exponent. In equation solver, it solves system of linear equation using ax equals b. NumPy functions are used for fast and accurate calculations. The graphical user interface. The class Numerical Methods app controls the entire graphical user interface. The main window contains two tabs, which is the root, finding methods, and the matrix operations. The applications uses labels, buttons, combo boxes, text areas, tables, and graph funnels. The interface is designed to be interactive and easy to use. In incremental method, function checks intervals one by one. If a sign change is detected, the program identifies a possible root. This method is useful for locating root intervals before applying more accurate techniques. In bisection, it functions repeatedly divides the interval into two equal parts. The midpoint is computed using the xr equals xl plus xq over 2. The interval containing the root is selected based on sign changes. Iteration continue until the error becomes smaller than the tolerance. In regular foci, it functions estimates the root using a straight line approximation. The formula uses both endpoints and their function values. Compared to bisection, this method often converges faster. In Newton-Raphson method, the Newton function uses tangent line to estimate roots. The formula is x1 equals x0 minus fx0 over df. This method converges very quickly when the initial guess is close to the root. Next is second. Second function is similar to Newton-Raphson but does not require derivatives. Instead, it uses two previous approximations to estimate the next root. This method is efficient and easy to implement. In graph visualization, the plot graph function displays the graph of the equations. Features include function curve, x and y axis, root markers, interval boundaries, and current approximation points. If detected roots are highlighted using color markers, the graph updates dynamically during iterations. This makes the solving process easier to understand visually. In Matrix tab, the Matrix Operation tab allows users to enter matrices manually. Users can resize matrices, choose operations, and compute results instantly. Results are displayed clearly in the result panel. The application also validates matrix dimension before computation. And error handling. This application includes handling using try and except. This prevents crashes and displays user-friendly error messages. Includes invalid equations, incompatible matrix sizes, division by zero, and invalid intervals. This improves the reliability of the program. Here's the clear matrix. So we run it. So here is the system. The drop-down method, we change the tolerance into 0.005 and then solve. As you can see, the group visualization, the bisection, we change it to bisection. And so on. So next is the matrix operation. So if we select the power, there is power adjustment. So I set also the rows and columns to set the size. and it's still working. So that's all for my Python preferred language, which is the Python. So next is the MATLAB. I will explain my MATLAB numerical methods application. This application was developed using MATLAB app use designer components such as UI figures, panels, grids, tables, access buttons, and drop-down menus. The purpose of this program is to solve different numerical methods, problems including root finding methods, matrix operation, graph visualization, iteration tables. The application provides a user-friendly graphical interface where users can input equations, choose numerical methods, and visualize solutions. First is the main function. Function numerical methods. This line defines the main function of the program. Everything inside this function belongs to the numerical methods application. Second is the cleaning MATLAB environment. These three commands prepare MATLAB before the application starts. CLC clears the command window, clear removes stored variable from memory, and closes all open figures. This ensures that application starts fresh every time. Third is the creating the main window. This creates the main application window. The properties define the window of title, window size, position in the screen, and background color. This serves as the main container of the entire application. Fourth is the main grid layout. This creates a grid layout inside the main window. Grid layout helps organize UI components properly. The layout has one row and one column. This acts as the base layout for the application. Fifth is the tab group. This creates multiple tabs inside the application. The program contains two tabs, which is the root tab and the matrix tab. The first tab is for root finding methods. The second tab is for matrix operations. This makes the interface more organized and easier to navigate. The sixth is the root finding tab. This creates a grid layout for the root finding section. The layout divides the interface into grid control panel, iteration table, and graph visualization. Spacing and padding are added to improve appearance and readability. Next is the control panel. This creates the control panel where the user enters data. Inside the control panel are users select equations, choose numerical methods, enter intervals, set tolerance values, and solve or clear results. Next is the equation dropdown. This dropdown contains predefined equations such as x cubed minus x minus 2 equals 0, and etc. The user may also choose custom to put their own equation. This allows the application to solve linear equation and etc. Next is the custom equation field. This text field allows user to type custom equations. Initially, the field is disabled, but when the user selects custom from the dropdown, the field becomes editable. Next is the method dropdown. This dropdown allows user to select different numerical methods, which are the incremental, bisection, regular foci, Newton-Raphson, and second method. Each method uses different mathematical approach to find the roots. Next is the input fields. These fields allow users to enter the lower bounds or initial guess, upper bound, and the tolerance value. The tolerance controls the accuracy of the solution. Smaller tolerance means more accurate results. Next is the buttons. The solve button starts the numerical computation. The clear button removes the iteration data, graph plots. This helps users to reset the interface. Next is the iteration table. This table displays the iteration process. The tables includes iteration number, XL, XR, XU, function values, approximate error. This helps users to uh, observe how the numerical methods converges the root step by step. Next is the graph visualization. This area is to create the graph area. The graph displays the equation curve, y-axis, x-axis, and the root points. Red dots are used to highlight the root visually, and this improves understanding of the solution. Next is the matrix tab. The second tab handles matrix operations. The program supports the matrix addition, matrix multiplication, transpose, determinant, adverse, adjoint, matrix power, and solving matrix equations. Next is the matrix inputs, matrix A, matrix B. These text areas allow users to input matrices manually, 1 and 2, 3 and 4. The matrices are later converted into MATLAB matrix format. Next is the callback functions. Callback connect buttons and wrap downs to functions. For example, clicking solve calls the solve root, and clicking compute calls the compute matrix. This makes the application interactive. Next is the toggle custom function. This function enables or disables the custom equation field. If custom is selected, the user can type an equation, otherwise the field is locked. Next is the get equation function. This function processes the equation entered by the user. The functions remove spaces, handles equation with equal signs, add multiplication signs automatically, converts operators into MATLAB element-wise format. Example, 2x plus 4 equals 0. It becomes 2 asterisk x plus 4 minus 0. Next is the parse function function. This converts the equation string into executable MATLAB function. For example, like this equation. This enables MATLAB to evaluate the function numerically. Next is the solve root function. This is the main numerical solver. The function reads user input, generates the graph, applies the selected numerical method, stores iteration data, and displays the root. In incremental method, the incremental method searches for interval where the sign changes. If fx1 times fx2 is less than 0, then roots exist between those points. Next is bisection method. The bisection method repeatedly divides the interval into two halves, like xr equals xl plus xu over 2. The interval is updated until the error becomes smaller than the tolerance. Next is the regular foci. Here is the formula. This method converges faster than bisection in some cases. Next is the Newton-Raphson. And here is the formula. This method is very fast but requires a good initial guess. And here is the approximate error equation. And here is the formula for second and the approximate error formula. Next is the matrix computation function. This function performs matrix operations depending on selected operation. MATLAB computes the addition, multiplication, transpose, determinant, inverse, adjoint, power, and equation. The result is displayed in the result panel. Next is the parse matrix function. This converts text inputs into actual matrix, MATLAB matrix. Next is the clear functions. This function resets tables, graph, matrix values, and results. This allows user to start a new computation easily. Next is the toggle power function. This function enables the power drop-down only when the user selects power operations. Otherwise, the drop-down is disabled. So, let's run the code. So, as you can see, the equations drop down. The method drop down. Customs, which is enabled if we click. Then the XL and XU. Then the tolerance, clear and solve buttons. And the graph visualizations and the iterations. So here is the example for quadratic equations. No root found in the interval using the incremental. But when you use the bisection, here, it's still running. But here's the roots. Next is the regular foci. Here's the roots. Here's the Raphson. Here's the root negative 1 point something. And here's the second. Negative 3 something. Next equation is for linear equation using the incremental. No root found in the interval, and the bisection is negative 1 point something. Next is the regular foci. Negative 2. Next is the Newton-Raphson. Still the same. And the second, still the same. Next is we solve the cubic equations using the incremental. But we changed the iterations, which is 0.005, found that 1.52. Next is the bisection. Next is the regular foci. Same. Next is the Newton-Raphson. Next is secant. Still the same. Next, we go to matrix operations. Here is the matrix drop down. When we click the power will be enabled. But when we click the addition, it will be disabled. And here's the buttons, compute and clear. We compute. Here's the result. And so on. Note that when we click the transpose something, it will be only the matrix A will be solved. So that's for the equations, and we clear it. We click the clear button, it will be dissolved. So that's all for my MATLAB applications. And that's all for my numerical methods project.